Hey guys. Well, the lesson here is known as rate laws and order of reaction. Now, for every reaction, there's a certain rate law. Now, what's so cool about this rate law is that with this rate law, you are able to find out if the concentration changes for the reactants, whatever it may be, how would the rate be affected by coming up with a mathematical equation. Oh man, mathematical equation, man, that sounds scary already if you don't if you think about it. So let's go on and take a look at the theory behind this, and then we're gonna look at a couple of examples, and yeah, let's do that. Now, the whole idea here regarding rate laws and the order of reaction is that this deals with concentrations. Now, what we understood from last lesson is that when concentration increases, rate increases. Let's take a look at this picture right here. So you're looking at reactants, okay, where blue and yellow will come together to create a chemical reaction. If you have a solution vessel, if you have a vessel right here where the concentration is not that much, well, the chances of them banging on each other with a certain force and the right orientation won't be that much. But if you were to increase the concentration, as you see right here, now you're talking, okay? Because the chances of this blue particle, finding the yellow particle with the right force for the right orientation is a lot higher. Therefore, the rate right here increases by a whole lot compared to this. Okay? So, that's something that we already know. That as concentration increases, the rate, increases. Because more frequent collisions. Now, with that in mind, okay, a factor where concentration reactant affects the rate of reaction, that it can be determined through experimental data. So in order to find these rate laws and order of reaction, you can't really just stare at an equation and be able to figure this out. No, that would be impossible. That's really not something that anybody have the capability of to do. So what you need to do is you need to do some experiments, and you need to gather experimental data or experimental evidence by having parameters set for, easy picking, I guess. We'll take a look at this in a sec, okay? We'll take a look at examples of experiment that you are going to do, okay, in order to find the rate law of a particular reaction. But before we do that, let's take a look at something known as order of reaction. Okay? The order of reaction pretty much summarize exactly what's happening in your reaction. It starts with zero order. Okay? But that's actually an easy one because it really doesn't matter. It's really independent here. And then we have, of course, first order, second order, and etc., which means there's third order, fourth order. As much as you can think. Now, what are these order? Man, that's confusing. Let's say, okay, you have this reaction right here. Okay? X plus Y will give you Z. And, of course, X has a certain concentration. Y has a certain concentration. Okay? And to get Z, there's a certain rate. There's a certain speed. And that all depends on what is the concentration of this and what is the concentration of that to determine. Now, there's also this guy right here. Okay? Now, what you see right here is called rate law expression. And the rate law expression is very, very, very simple. dictated by the reactants right here is that the rate of any reaction, the speed of any reaction, is equal to some sort of rate constant. This rate constant is dependent on a certain temperature. Now we know temperature plays an important role in terms of rates. Okay? Temperature plays a huge role in rates because when temperature increases, these particles start going crazy and they will hit each other with a lot of energy. As a result, the reaction will increase in speed. So K is temperature dependent because when temperature increases, K is not the same K anymore. It's going to be a different value. It would be a higher value. Okay? So in a rate expression, rate is equal to some sort of rate constant, coexist with a certain temperature, times the concentration of X to the power of A. These are called order, okay, rate order, okay, or order of reaction, okay, and this is based on what this is, and we'll see in a sec how to determine what A and B is going to be. Now, since we have two reactants right here, you're going to have the concentration of the second reactant, Y, to another, I guess, reaction order. Okay, so reaction order here, A, coexists, of course, with the reactant X, and the reaction order B coexists with the concentration Y. If you were to add A and B together, we call that the overall reaction order. And the overall reaction order play a huge role in terms of the speed of your reaction. So this is your rate expression. Okay? So I guess if I were to give you an example right here, very quick example, like how you have H2 plus O2 will give you H2O, if you were to set up a rate expression for this, is that the rate here is equal to some sort of constant at a certain temperature, okay, times the concentration of H2 to a certain reaction order plus the concentration of O2 to a certain reaction order. Now, you notice that I use M and N. Doesn't really matter in this case. Okay, basically is a certain number here. Could be 0 too. Okay, so let's take a look at these reaction order. Okay, so when the order of reaction is 0, so you have a rate expression that may look like this, where the rate is equal to some sort of rate constant times a certain reactant to the power of 0. Anything to the power of 0 will equal to 1. So what that means is that the rate in this case is pretty much equals to the rate constant itself. What does that mean? What that means, it doesn't matter what the concentration is. It doesn't matter what the concentration is. Because whatever this number is going to be, it's going to be 1. Because the order is a 0 order. The speed of this reaction is exactly what the rate constant is going to be. So in this case, we say in description right here, the rate is independent of X. Had nothing to do with the concentration. Changing the concentration will not speed up this reaction. Now, notice I gave you right here that the unit for K in a 0 order reaction. So the unit of K of a 0 reaction is exactly what the rate is, which is, of course, molarity per second. Okay, the concentrations per second. Let's move on to the first order. in terms of the first order of reaction, K will have a unit of per second. Now, nothing per second. I didn't say anything about concentration per second or liters per second, moles per second. No, just per second. So whenever you see a rate constant, if somebody would introduce you, this is the rate constant for this reaction, and it says this constant is going to be per second, you can bet that this is a first order reaction, and a first order reaction is dependent on the actual reactants. Okay? However, it is just whatever the reactant is, because it is to the power of 1, okay, which makes it first order. Okay? So the concentration of X is as this. So the rate is directly proportional to what X is. What that means is that if X increases, rate increases. X decreases, rate decreases. When it decreases and increases exponentially? No, because the exponent here is as a 1. And that all deals, of course, with what this is too. Okay, to determine what the rate is. You'll see lots of examples with this in mind. Okay. Then, of course, there's second order of reaction. Now, if you see a second order of reaction, you'll notice that the unit for K is going to be liters per mole second. It's almost like inverse molarity per second. Here it is. Okay, that the rate is determined by the square of the X concentration, whatever this thing is, to the power of 2. Double it. I shouldn't say double it. It's not times 2. It's power of 2. I'm sorry, to the power of 2. If this is an 8, then therefore it's going to be 64. So the rate will obviously be a big number, depending on what this is. It's going to be a lot larger than what X is going to be. Okay? Like I said right here, if the concentration of X is triple the times, the rate will increase by a factor of 9. Okay? Now, you can also write it like this. Of course, it doesn't have to be just X. If this reaction has 2 reactants, okay, both to the power of 1, this is also known as a second order. All right, so this is still a second order. Same with this. If you have a rate law, if you have a rate expression where you have 2 reactants, hey, if Y is 0 order but X is first order, overall is still first order. So something to keep in mind. Now, and we talked about like rate order here, 0 order, first order, second order. We know their units, fine and all. Okay, certain reaction will have a certain order of reactions. And, lucky enough, if it was 0, then hey, there's really nothing much to worry about. But of course, most of the time it's not going to be. And we will have to see exactly how reactants concentration will affect the rate by looking at this problem. Here's a very nice equation. I'm not going to even try to dissect that. But it's actually a very nice way. Let me just, if you really want, of course, I can draw this for you. For you have BF3. We all know that boron is a very special atom where it can be surrounded by 6 valent electron and it'd be fine. Okay? Ammonia, on this case, it won't be fine. It has to be surrounded by 8. So, hey, boron don't mind being surrounded by 8 electrons. It doesn't. It will love it. Okay? He said, right now I have 6, but I don't mind having 8. Where am I going to get 8? Well, this nitrogen says, hey, I have these 2 lone pairs. You want? Take them! To give you this little complex right here. Okay, so that's the reaction. Again, this is not important, have nothing to do with this question. So let's take a look at this question right now. So remember what I said, that in order to find the rate law, you need to do experiments. You need to test things out. And this is a perfect scenario in terms of how to test the rate of this out. I did 5 different experiments. What I did is that I changed BF3 in terms of concentration. I changed NH3 in terms of their concentration. Then, of course, I look at the speed. To find this out, I sort of have to figure out how to monitor this guy. How to monitor the production of this guy, or monitor the decreasing of this guy or this guy. Basically, to find this, I need to have some sort of indication. It could be a color change. It could be some other change to tell me, yes, the rate of this reaction at these concentration is this molarities per second. It's always going to be molarities per second, but that's not the important part. The important part is, how am I going to set this experiment? How do I set these experiments up? Well, this is what you should do if you're asked to do something like this for real. Between experiment, you should keep at least one parameter constant. Now, this reaction involves 2 reactants. Okay, so from experiment to experiment, you should keep one of the concentration constant. And we did. So if you look at experiment 1, experiment 2, we kept BF3 the same number, 0.25 molar. And what we did was we changed the concentration of NH3 by half. And we noticed that if we kept this the same, but we changed this by half the amount, the speed also changed. How much did it change? Kind of by half too. Wow, that's cool. But we can't figure out a rate law just by that. We have to do more. And that's experiment 3 and 4. Okay? What we did with experiment 3 and 4 is that now we kept NH3 the same. Kept them constant. Change BF3. Now, the numbers are not that great to look at this time because it's not like we chop it by half. We actually increased it by 0.15 of the molarity. Okay, and we noticed that by increasing BF3, rate increases. That's sick. Well, for some reason, actually not for some reason, most of the time, we like to repeat some experiment with other parameters. So in terms of experiment 5, we kept ammonia to be 0.1 molar. We sort of dropped BF3 to a smaller number than 0.2. And if theory holds true, okay, increasing BF3 will increase the rate, while decreasing BF3 should decrease the rate, right? And it did. So I was able to collect all these data. Now with that, I may answer these questions. This being the most important one of them all, because this question, along with this, will show you exactly how the rate of this reaction will relate when the concentration of these participants changes. Let's do a rate expression for this. The rate expression for this is that the rate is equal to K times BF3 to the power of, let's say, A times NH3 to the power of B. There's three things here that is within my interests. K, A, and B. Because if I can find out what these numbers are, it doesn't matter how these changes, I will still get the rate. And let me show you how by doing question A in this blank piece of paper right now. Okay, what is the rate law for this reaction? What is the rate law for this reaction? Basically, in this question, I'm looking for A and I'm looking for B. Okay, how am I going to do that? There's many strategies. Some people can eyeball it and be able to find out exactly what it is. Some people, maybe like myself, needs to write everything down. This is the strategy. You're going to pick two experiments. You're going to make sure that one of the parameter is constant. Okay? I will pick experiment 1 and 2. Because I know in experiment 1 and 2, BF3 is kept constant. Now, I'm going to write the rate expression with, let me just write it here. So rate is equal to K times BF3 A times NH3 B. I'm going to write this down. I'm going to relate experiment A, 1 and 2 together. So let's go with experiment 1 on top. So the rate here is 0.213. That's the speed of this reaction. That is equal to some sort of K times BF3 in this case is 0.25. A times 0.25. So for experiment 1, concentration of NH3 is 0.25 B. So that's through experiment 1. Oh. Now, I'm going to relate this as a ratio. I'm going to relate this as a ratio for experiment 2. Experiment 2 is the rate is 0.1065. That is equal to K times BF3, in this case, is 0.25. That was the one we kept constant purposely, times 0.125. So this right here is experiment 2. So we're relating the ratio of experiment 1 and experiment 2 together through its rate, through their concentration. Now, if these, it is actually, this is really one dividing it by the other, that K should be crossed out. They're going to be the same number. 0.25A and 0.25 to the power of A should also be crossed out because these are going to be the same number and they're going to be 1. Can't cross these two out. No, because these are not the same number. Okay, to the power of B, it's going to be different. This, we can start dividing. So 0.213 divided by 0.1065 is equal to 2. 2 is equal to, well, what you can do here under the law of logarithm, not logarithm, the law of exponent, the law of exponent, I'm a little ahead of myself, you can divide these two, okay? Because this right here is basically that. So you can quickly divide 0.25 divided by 0.125, and that would be also 2 to the power of b. So 2 to the power of something is equal to 2. Well, that something has to be 1. There you go. Look at that. Look at that. We found out how to find A. I'm sorry, we found B. We found B. Next, let's find A. To do that, we need to select 2 experiments where NH3 is going to be kept constant. Because if you see right here in this one, we kept BF3 constant. By keeping these constant, they scratch out. Right? Now we want to keep NH3 constant. So that way these scratch out. So let's do that right now. Let's use another color. Okay. So let's relate in this case experiment 3 and 4. Doesn't really matter. Okay, really doesn't matter what you pick. So let's take a look at experiment 3. Experiment 3 is 0.2 is equal to K times 0.2 to the power of A times 0.1 to the power of B. Okay, let's take a look at experiment 4. Experiment 4 is 0.35 in terms of speed is equal to K times 0.35. Oh, wait, what am I doing? 0.35. Must be looking at the wrong thing. Same here. Why did I look at the concentration? This is supposed to be the rate, dude. 0.0682. 0.1193. Whew. That was a scare. All right. Okay, I put it together. Okay. Let's simplify. So 0.08682 divided by 0.1193, that is 0.572. This may not be a good idea to pick. This may be a lousy idea to pick. All right. Let's cross certain things out. Okay, we know these cross out. We know these cross out. So what I have here is 0.2 divided by 0.35. Okay. Luckily, it is also 0.57. I guess 1 in this case to the power of A. So A will be 1. Okay. These numbers are pretty much the same number. Experiment 3 and 4 is a bad idea to pick. I should have picked experiment 3 and 5. I think 3 and 5 would have been better. Or 4 and 5. I think 4 and 5 would have been excellent too. Yeah, 4 and 5 would have been great. I should have picked experiment 4 and 5. But it works. Okay, it works. We're done. Okay, so the answer for part A is that rate is equal to K times BF3 to the power of 1 to NH3 to the power of 1. That's the answer for part A of this question. Pretty sick, huh? So what does part B want? Okay, let's write it down here. Let's write the answer down here. So rate is equal to K BF3 to the power of 1 and times NH3 to the power of 1. Now, since it's the power of 1, you don't really need to put that 1 there. You can put nothing there. By putting nothing there, it's 1 by default, right? All right, B. What is the overall order of this reaction? Well, that's simple. Isn't it just adding those exponents together? Yep. 1 plus 1. The overall is 2. So it's a second order overall reaction. So the changes of concentration of both reactant will cause an exponential change to the rate. That's this scenario right here. Huh. All right, part C. As I said, this one is a big deal too, because part C, you are going to find K. You need to find what K is. So let's go back here. Okay, let's go back here. Let's erase all of this. So this is the rate expression. Okay, there's a reason why I kept this. This is the rate expression. What you can do right here is that you can go through those experiments. Experiment 1, 2, 3, 4, 5. And you're going to plug any one of those into this equation right here. And solve for K. All right. 1, 2, 3, 4, 5. What do you guys like? Well, it's not like you guys can answer me through this. This is pre-recorded. I like 5. Okay, I like 5. I always like that number. So let's plug experiment 5. So 0.175 is the rate. Oh, wow. No, it's not. It's 0.0596 is the rate. I almost did it again. That is equal to K times 0.175 to the power of 1 times 0.1 to the power of 1. What is K? Well, 0.0596. That will be divided by 0.175 times 0.1. And K is 3.41. That's K. Okay, let's put this back in right here. 3.41. Now, what people will do here is that they will just fix the rate law. Because right now your rate law is a little bit more complete. That for this reaction at a certain temperature, remember, it's a certain temperature here. T is very, very certain. Because if T changes in any of these reactions, this right here is incorrect. Okay, K will not be the rate constant if your experiment changes in temperature. Let's say you decide to do this at 25 degrees Celsius, but you did this at 30 degrees Celsius. Then things will not make sense. You will have to throw this experiment in the garbage or don't use this. Because all of these has to be done at a certain temperature. So let's fix part A. That rate is equal to 3.41 times BF3 to the 1 times NH3 to the 1. This is a complete rate law expression for this reaction. All right. We can do part D. Part D is a very nice question. Part D says, all right, if I have BF3 at 0.5 and NH3 at 0.6, what's my speed? Hey, since we already found out what the rate expression is, all you have to do is plug this here, and you'll find out what this is. Let's do that. So rate is equal to 3.41, okay, times 0.5 to the power of 1 times 0.6 to the power of 1. So rate is therefore, let me grab my calculator, is 1.023 molarity per second. Look how useful that is. Okay? By doing these series of reactions. Well, not reaction, by doing these series of the same reaction, by changing the concentration of this or this, you are able to find the equation necessary to find the rate at whatever concentration of BF3 or NH3 you wanted. You can put whatever number here and here and you'll find the rate. You'll know how fast this reaction is going to be. That's how powerful rate law is. I hope you'll get it, because there's a couple of more questions I want you to do. Here's one right here. Okay. Here's another right here. This one is tricky. This one is really the same thing as the previous one. Okay. Keep these constant, change this, what would it be? Keep these constants, change these, what is it going to be? Same thing as the last question. But this is big time. Why? Because if you look at the rate expression right here, is that rate is equal to K times IO3, iodate, to the power of A, 2 iodide to the power of B. Oh no. Oh no. There's 3 reactants. Potentially it can be a third order reaction. But who knows? Maybe it's not. Maybe one of them is a 0, right? Now, to do example 3, you need to keep in mind a couple of things, okay? If you're trying to find A, you have to make sure you pick 2 experiments where both this and this is constant. 1 and 2 is a good one. If you're trying to find B, you have to make sure that this and this is constant. 1 and 3 is a good one. If you're trying to find C, you have to make sure that A and B is constant. These 2 are good ones. All right. So let's do that, and we'll take it up the next day. And yeah, there's a final question right here, just like example 1. So look over example 1, see exactly what we did. Go back and watch this again if you like. Oh my, this should put you to sleep. And see if you can do question 2 and question 3. All right. I'll see you later. Bye.